Today we're going to look at galaxy formation, and this is in the light of a new theory. We've looked in the past at the problems with the Big Bang theory, which is being contradicted by observational evidence from the James Webb Space Telescope. The actual distribution and appearance of galaxies is not consistent with the prediction of a uniform distribution of galaxies in the universe, which would be expected from the Big Bang. The Big Bang violates the law of conservation of energy. The Hubble tension is a discrepancy in the measurement of the expansion of the universe. And the description of the cause of the cosmic microwave background from the Big Bang theory is most unsatisfactory. And we have no explanation for dark matter and dark energy. So previous talks I've given on the subject had these conclusions: that the universe is finite with a space boundary. Galaxy formation takes place from energy released from expanding curved space. The universe is expanding at a constant rate over time and distance. And the cosmic microwave background radiation is coming from radiating matter, which is held at the event horizon of the universe. And we have also measured that the Milky Way galaxy is 26 million light years from the center of the universe, which puts us quite close to the center. So here we have a graphic describing the universe, showing the red dotted line being the space boundary. And it shows space curvature parallel to the boundary, but no space curvature in the radial direction. And the proposed mechanism for matter formation is that we have to consider, following the Einstein equations of general relativity, the effect of the expansion of space on the space curvature, which results in matter formation. And you can see in this graphic that the curvature is will be greatest closer to the center, and this then leads to a hypothesis about the formation of galaxies and the galaxy density varying with distance from the center of the universe. So here we have some real observational data, which I collected about 20 years ago using the NASA extragalactic database. And it shows a count of the number of galaxies in each distance band out to around 550 million light years. And this plot was obtained by counting the specific galaxies, the 110,000 galaxies, out to that distance from the NASA extragalactic database data. And this profile is going to be used to form the hypothesis that there is a relationship between the number of galaxies and the distance from the center. And if you say that the number of galaxies is going up in a linear way, you can rephrase that to say that the number of galaxies out to a certain distance goes up as the distance squared. So although this is a very local view of the galaxy distribution, we're going to use that as the basis for a broader assumption about galaxy formation. Now, this is just a reference showing the actual data as downloaded from the NASA Extragalactic Database, and each one of these lines of data represents one galaxy. And that was accessed in January 2008. We'd also like to be able to explain some of the features of galaxy distribution, in particular the voids that appear. And this is a plot of the 2DF Galaxy Redshift survey, and you can see there's a certain texture to galaxy positions which we'd like to be able to explain. So first of all, we look at the event horizon, and the hypothesis that there is enough mass in the universe to form an event horizon is analysed here. And we've taken 28 billion galaxies, and those galaxies are assumed to be typical of the Milky Way or Andromeda in mass, 2 times 10 to the 42 kilograms. But the important value on this page is the total mass, and that's 5.6 times 10 to the power 52. And it's that mass, regardless of how many galaxies of various sizes it could be made up of, is the mass which creates an event horizon at 8.77 billion light years. So are those numbers realistic, 28 billion galaxies? Well, this is an extract from a website called the Atlas of the Universe. And you can see here there's a much larger estimate put on the value of the number of large galaxies, 350 billion, which seems much greater than the 28 billion that we've assumed. But when you look at the value given for the number of stars in the visible universe, that's 3 times 10 to the 22. If we were to assume that each one of those stars was a solar mass, which is 2 times 10 to the power 30, you would get 6 times 10 to the power 52 kilograms. And that then corresponds to the mass that we're assuming within our event horizon. So taking our model in which we lay out those 28 billion galaxies by distance, we're saying that the number of galaxies increases steadily. What this is saying, in fact, that if you take a certain distance out, then the number of galaxies within this area is proportional to the square of the distance from the center. So that's the model, and this is the model which actually we take at the formation of the event horizon. So we'll see later on what happens to the galaxy distribution once the event horizon forms. So from the event horizon time, we go forwards in time and backwards in time to plot the effect on the galaxy distribution. So again, referring back to the Atlas of the Universe, there's an analysis which was of the universe out to 2 billion light years, and they have estimated roughly 25 million large galaxies within that distance. So we're going to use that as an aid to our calculations. So we want to know when the event horizon formed. And we're going to assume this formula, which is n equals ax squared. So n is the total number of galaxies. X is the distance to the out of the galaxy field, and that's measured in millions of light years. So if we're taking the whole galaxy field out to the event horizon, that's out to 8,770 million light years. And our number of galaxies is 28 billion. So that gives us a value for A of 364. So starting with that formula, and A we refer to as the distribution coefficient in the formula, we can see that our current observations show that 25 million galaxies out to 2 billion light years. So if we go back to the formation of the event horizon, those 25 million galaxies, taking that value of n, would predict a value of x of 262 million light years. So what that says is at the time of the formation of the event horizon, those 25 million galaxies were located within 262 million light years from the center. So now we know that they're currently out to 2 billion light years. So how long does it take for the universe to expand from 262 million light years to 2 billion light years at the rate of the factor E, 2.72 every 14 billion years? And the estimated time is 2 lots of 2.72, which equates to 28 billion years. So this is a picture of the number of galaxies at a time 28 billion years ago. And I've put the number of billions of galaxies in each band, and it's color-coded really to just illustrate what happens to that part of the galaxy field as the universe expands, and to illustrate the effect of the event horizon. So what's going to happen? Well, space is expanding, and the rate of expansion is the same everywhere, but the actual expansion effect, the recession velocity for each galaxy, is proportional to its distance from the center. But given that the galaxies cannot cross the event horizon, this means that the galaxies are prevented from crossing the event horizon. And you can see the effect. So now we've gone from 28 billion years ago in the previous slide to 14 billion years ago. So all of these numbers of galaxies have moved out by a factor of E, 2.718. But as you approach the event horizon, the galaxies are held, and the rate of the expansion is diminished. Incidentally, this also gives an illustration of the effect previously attributed to dark energy, because the recession velocity of these galaxies will be less than expected. And this shows the current distribution. So We've now moved the galaxies out due to the expansion of space. And the 25 million galaxies that we referenced are located here out to 2 billion light years. And this is the entire field colored in light blue, stretching right out to 8 billion light years. So whenever we talk about observational distance rather than the real physical distance that we've been dealing with, we have to recognize that the distance ladder that we talk about is really a look back time ladder, because all the measurements that we make, redshift, luminosity, all are dependent on the actual travel time of the light radiation through expanding space. So what happens is that if you have an object which is physically 1 billion light years away, we would measure that distance as 1.038 billion years of look back, because in that time, the universe has been expanding. And in a previous talk, I've calculated from the expansion formula the way of converting between the distance x and the look back time t, and those formulae are shown on the page. But what it means is that for distances of 1 billion, 2 billion, it doesn't make much difference. 2 billion light years, look back time 2.1.7 billion years. But as you go further out, and as you get to the event horizon at 8.77 billion light years, the look back time for that is actually 13.8 billion years. So we can then look at our galaxy distribution as it is now and show it in relation to the look back time, which slightly changes the distribution, but you still have a situation where the galaxy distribution is heavily skewed towards the event horizon. Remember in all of this that the Milky Way galaxy is only 26 million light years from the center. So all the observations that we make of this galaxy field are made from the vantage point, which is very close to the center. So we'd like to understand how the galaxy formation profile that we've shown there arrived over time. And to do this, we're going to suggest that this relationship n equals ax squared applies not just to the galaxy distribution at the time of the formation of the event horizon, but it also applies during the earlier periods of formation. And so we take a reference time, TR, which is when the event horizon formed. So at that time, XR is 8,770 million light years. NR is 28 billion galaxies. And AR, our distribution coefficient, is 364. And we're assuming throughout all of this that matter formation is proportional to the volume of the universe, which is not unreasonable given that it's matter being released from the universe as a whole. And what that means is that because space is expanding by a factor E every 14 billion years, that the volume of the universe is going up by a factor of E cubed. So that means that our N value is going up by a factor of around 20, E cubed. And we know the distances are going up by a factor of E every 14 billion years. So that means that the distribution coefficient, starting from 364 at TR, will reduce by the factor E every 14 billion years. So turning that into a table, you can see that starting from 28 billion galaxies at the time of formation of the event horizon, we reduce this by a factor of 20 every 14 billion years until 140 billion years ago, we had just one galaxy. So this is the first galaxy to form. So our distribution coefficient, we reduce by a factor of 2.71 every 14 billion years. And we can use that to define the minimum position for galaxy formation. So this is worked out by using the formula n equals ax squared, where n is 1 because we're talking about one galaxy formation at a distance x. And so from the formula, we can get the value of x for our minimum position. And so 28 billion years ago, that would have been at around 52,000 light years from the center. The maximum position for the galaxies that we're interested in inside the event horizon, we take that at 8770. And going back in time, we're taking the view that when the event horizon formed, those galaxies were part of a set of galaxies that were located out to 3226, 14 billion years previously. So we're taking the extent of the galaxy formation to be moving outwards. And that's for a good reason, because the curvature of space is greatest close to the center, and there will come a point where there's insufficient curvature to trigger galaxy formation. So this tracks the upper end of the range of formation. And I've shown the position of the Milky Way because that is currently located at 26 million light years. So going back 28 billion years, we would be 3.5 million light years from the center. And the reason why the list in the last column stops is because the Milky Way position at the time indicated has to be greater than the minimum position. So beyond that, it ceases to be the case. So that's why we hypothesize that the Milky Way formed between 56 and 70 billion years ago. So from the model, we're taking the view that formation at a time t takes place between the minimum and maximum positions. It gives us an estimate of the time of formation of the Milky Way galaxy. It suggests that the first galaxy formed about 140 billion years ago at a distance of 2.9 million light years from the center. And we propose that galaxy formation happens over a range of distances from the center, overlapping the existing galaxy field. So it's not the case that galaxy formation starts at the center and works outwards, with that being a prediction of the age of the galaxy. That doesn't seem to work. And we can say that the distance from the center of the universe is not a reliable guide to the age of the galaxy. There's evidence that galaxy formation stops once the energy from the release of space curvature has been released into matter formation. There's a couple of pieces of evidence of that, which comes from galaxy distributions. So, for example, if you get a cluster of galaxies forming, they will release the tension in the medium of space, leading to a tendency for galaxies not to form subsequent to that in the local vicinity. But this effect is taking place moving from the center of the universe, and we can hypothesize that around 42 billion years ago, galaxy formation was stopped out to 30 million light years. Then 28 billion years ago, it would be stopped out to 81 million light years. 14 billion years ago, it would be stopped out to 222 million light years. And currently, galaxy formation is stopped out to 603 million light years. And this is all, it's a kind of saturation effect of galaxy formation. But from the model, we can see that this effect of the formation stopping 42 billion years ago, we can say that there were 120,000 galaxies out to 30 million light years, and that region, without further galaxy formation, has expanded out to 600 million light years. And that corresponds pretty well with the observational data. There's also the point that the closest galaxy to the center is around 9 million light years. So if we assume that formation closest to the center stopped around 56 billion years ago, the minimum position then was 0.142 million light years, and that would now equate to 7.75 million light years. So that's then of the same order of magnitude as the observed value for the closest galaxy. So just to recap, what we're saying about the galaxy formation process is that galaxies form at points in space. This is not from the collapse of a dispersed cloud, as proposed by the Big Bang theory, which would have produced a galaxy pattern which is pretty uniform and complies with the cosmological principle that the universe is the same everywhere. And it's clearly not. Galaxies form from energy released from the expansion of curved space. So this this effect of the different curvature of space as you go out in distance leads to the reasonable hypothesis for this relationship n equals ax squared that we've been using. The number of galaxies in the universe increases by a factor of 20 every 14 billion years, and that once formed, the galaxy position is affected by the expansion of space. And that means that its distance from the center increases by the factor e every 14 billion years. When a galaxy forms, it reduces the tension in the medium of space, suppressing the formation of other galaxies nearby, and this leads to galaxy voids, which are observed. The actual galaxy formation event, where the energy is released from the fabric of space, produces neutrons, and that leads to the formation of a cloud of hydrogen, helium, and dark matter, and dark matter is bonded neutrons. The galaxy formation event also emits intense gamma radiation and cosmic rays. And we've also previously explained that spiral galaxies are formed from two gas clouds under the effect of gravity and the expansion of space, which stretches the spherical shape so that the remote sides of the galaxies form the spiral arms.